In a previous video, we said that excretion includes the steps of filtration, reabsorption, and secretion. In our previous videos, we looked at glomerular filtration. Here, we want to take a look at the reabsorption of materials back into the bloodstream. Most of what gets filtered out up at the glomerulus, we want to retain in the body, like water, glucose, amino acids, most of our sodium, most of our potassium. We don't want to lose those things. We want to pull them back into the blood. Tubular reabsorption is the process by which we retain these chemicals and, by doing so, also retain our blood volume. Tubular reabsorption is a selective process, meaning that we only pull certain or select chemicals back into the blood. We're not going to reabsorb everything, only certain things. If the kidneys are healthy, virtually all organic compounds, like glucose and amino acids, are going to be reabsorbed. We shouldn't find glucose or amino acids in the urine unless something is wrong within the body. However, water and ions, like sodium and potassium, are continuously regulated and adjusted by the kidneys. We should be able to find some sodium and potassium in the urine, and depending on what's happening in the body, those levels may increase or decrease. Depending on what substance is being transported, transport may either be active, that means requiring the use of ATP to move materials up or against their concentration gradient, or passive, using diffusion, facilitated diffusion, and osmosis to allow molecules to move back into the blood without the use of energy, moving down their concentration gradients. Sodium reabsorption is almost always an active process. The reabsorption of sodium occurs in most of the nephron tubes, meaning we're constantly reabsorbing sodium in our proximal convoluted tubule, our loop of Henle, and we can adjust sodium reabsorption in the distal convoluted tubule and in the collecting duct. We reabsorb sodium along the length of most of the nephron. The reabsorption of sodium by active transport provides the energy necessary for transporting almost every other substance that needs to be reabsorbed into the blood. This is called secondary active transport. In secondary active transport, the energy used to move one chemical drags a second chemical with it. We directly spend energy to move one kind of chemical, like sodium, and the movement of sodium drags a second chemical, like water or glucose or amino acids, with it through this secondary kind of transport. The movement of sodium back into the blood establishes an osmotic gradient. Water follows that salt back into the blood because of that osmotic gradient. This is our rule of thumb, where water follows salt. If I reabsorb sodium, I'm also going to wind up reabsorbing water along with it. Water can also be passively absorbed through certain protein channels called aquaporins. Aquaporins because they are specific for allowing the movement of water. Aquaporins are always present in the proximal convoluted tubule, and because of that, we're always absorbing water in that proximal convoluted tubule. Normally, those aquaporins are usually not found in the surface of the distal convoluted tubule or the collecting duct. However, if a certain hormone, like antidiuretic hormone, is available, it causes extra aquaporins to migrate to the surface of the collecting duct and increase water reabsorption. In doing so, we increase the amount of water that comes back to our blood, which increases our blood volume, which eventually leads to an increase in blood pressure as well. Most reabsorption takes place in the proximal convoluted tubule. This includes all of the glucose, all of the amino acids, and about 65% of the sodium and water that's going to be reabsorbed into the body. It also includes reabsorbing about 50% of the urea that we're trying to excrete out in the first place. We don't want that urea in the blood, so most of it is secreted back into the urine later on as it moves through the nephron tubes. Water is reabsorbed on the descending side of the loop of Henle, but not on the ascending side, because on the ascending side of the loop of Henle, there are very few, if any, aquaporins. Because we're constantly reabsorbing water on the descending side of the loop of Henle, it sets up a difference in concentration gradient. Because of that, on the ascending side of the loop of Henle, sodium can be reabsorbed in a passive kind of way. Here, the lack of water, because water has been reabsorbed on the descending side, means that sodium concentrations in the nephron tube have been increased, so that on the ascending side of the loop of Henle, sodium can now move down its concentration gradient and move back into the blood. This is possible because of that loss of water on the descending side of the loop of Henle. Further up on the ascending side of the loop of Henle, we absorb additional sodium as well as potassium and chloride ions. After the loop of Henle, filtrate starts to move into the distal convoluted tubule. The reabsorption in the proximal convoluted tubule and loop of Henle is relatively constant. However, reabsorption in the distal convoluted tubule is under hormonal control and allows us to adjust and refine what we're pulling back into the body and what we secrete into the urine to push out of the body. If ADH is traveling through the bloodstream, it increases the number of aquaporins, which increases water retention in the body. If aldosterone is available in the bloodstream, it causes additional sodium to be reabsorbed in the distal convoluted tubule. That reabsorption of sodium drags water along with it and further increases blood volume and blood pressure. If ANP is traveling through the bloodstream, on the other hand, it inhibits sodium reabsorption in the distal convoluted tubule. We don't reabsorb as much sodium, and so we don't reabsorb as much water. More water winds up in our urine, and this allows us to increase the amount of water leaving the body and decrease our blood pressure overall. And the hormone PTH, or parathyroid hormone, increases the reabsorption of calcium from the distal convoluted tubule. The more PTH we have, the more calcium we reabsorb.